Your Python script is slow, so you split the work across 4 threads. And nothing happens. Same runtime, plus or minus noise. So you swap threads for processes, and suddenly it's 3.5 times faster. Then a colleague does the exact opposite with their code. Threads give them a 12x win, and processes would have been completely pointless. Today we're going to run those exact benchmarks live, and by the end you'll be able to pick the right tool in about 5 seconds. And I want to be upfront about the method. Every number you're about to see is a real measurement from this machine, a 12-core box, using best of 3 runs to squeeze out noise. No hand-waving. No, it depends without saying on what. We measure first, then we explain, then we turn it into rules you can actually use at work. First, what are these 2 things actually? A process is a running program with its own private universe, its own memory, its own Python interpreter, its own everything. 2 processes can't touch each other's variables even if they try. Threads live inside a process. 1 memory space, shared by all of them. Every thread sees the same variables, the same objects, the same heap. That difference drives everything else. Threads are cheap to start and communication is free. You just read the same variable. But sharing memory means they can corrupt each other's data, and, in Python, it means they all answer to 1 gatekeeper we'll meet in a second. Processes are expensive to start, and talking between them means serializing data across a boundary. But each one has its own interpreter, and that buys real parallelism. You can literally watch the difference in your task manager, by the way. Run a threaded script, and you'll see 1 Python process, maybe bouncing around 15% CPU on a 12-core box, because 1 core is all the GIL lets it use. Run the multiprocessing version, and 4 separate Python processes appear, and the total CPU actually climbs toward 4 full cores. It's a surprisingly good gut check when you're not sure your parallelism is real. Now the gatekeeper. CPython has a global interpreter lock, the GIL. The rule is 1 sentence. Only the thread holding the lock can execute Python bytecode. Doesn't matter if you have 12 cores and 12 threads. Inside 1 Python process, bytecode runs 1 thread at a time. They take turns, quickly, but turns nonetheless. But, and this is the detail the whole video hinges on, a thread releases the GIL when it waits. Waiting on a network response, on a disk read, on a sleep. The moment a thread blocks on input-output, it hands the lock to someone else. So the GIL punishes computation, but it forgives waiting. Keep that asymmetry in mind, because you're about to see it in the numbers. And in case you're wondering why Python would tie 1 hand behind its back like this, it's not an accident, it's a trade. CPython manages memory by counting references to every object, and with a single global lock, those counts never need expensive per-object synchronization. That makes single-threaded Python faster and makes C extensions vastly easier to write correctly. The GIL is the price, and for code that waits more than it computes, you barely ever pay it. Benchmark 1, pure CPU work. Here's the setup. Crunch sums I times I over a range. 40 million iterations total, no files, no network, just arithmetic. And I've set repeats to 3, because we'll take the best of 3 runs for each configuration. That's standard benchmarking hygiene. The minimum time is the one closest to the true cost. 3 contenders. Bench single just calls crunch with the full 40 million. Bench thread splits the work 4 ways across 4 threads, starts them all, waits for them all. If threads ran in parallel, this should be about 4 times faster. And bench processes is character for character the same code, with process instead of thread. Same split, same start, same join. That symmetry is deliberate. Whatever difference we measure comes purely from threads versus processes, nothing else. The harness. Best of runs each benchmark 3 times and keeps the minimum. And note the if name equals main guard at the bottom. On Windows, that's not optional for multiprocessing, and I'll show you exactly why it exists a bit later. Let's run it. This crunches 40 million numbers 9 times over, so give it a moment. And here come the numbers. 1 thread, 3.33 seconds. For threads, 2.95. For workers, and we gained barely 10%, which is scheduler noise, not parallelism. nowhere near the 4x we asked for. And 4 processes, 0.96 seconds. 3.5 times faster. Same code, same machine, same 40 million iterations. This is the GIL, caught red-handed. Our 4 threads were real operating system threads on a 12-core machine, but only one at a time was allowed to execute bytecode, so they queued up for the lock and effectively ran sequentially. The 4 processes each had their own interpreter, their own GIL, and genuinely ran on 4 cores at once. For CPU-bound Python, threads simply do not deliver parallelism. Benchmark 2, and now the tables turn. Input-output bound work. Fetch simulates a network call. It waits 0.4 of a second, exactly like an API request would, and I'm using sleep so the benchmark is perfectly reproducible. The comment is the whole point. While a thread waits, Python releases the GIL, and we have 20 of these calls to make. 2 strategies. Sequential fetches the 20 URLs one after another, simple and honest. 20 times 0.4 is 8 seconds of waiting. Threaded spins up 1 thread per URL and lets them all wait at the same time. Run it. The sequential version is doing its 20 polite little waits, one at a time, 8.13 seconds, right on schedule. And the threaded version, 0.69 seconds, 12 times faster. All 20 waits happened simultaneously because none of them needed the GIL while they waited. Same threads that were useless 2 minutes ago just delivered a 12x speedup. Nothing about threading changed. The workload changed. And that's the entire secret. Web scrapers, API clients, database-heavy services, log shippers, all of that is dominated by waiting, and threads eat that kind of work for breakfast. And by the way, real multiprocessing here would be strictly worse. 20 processes cost far more to start than the waiting they'd save. 2 practical notes before we move on. In production, you wouldn't hand-roll thread lists like this. You'd use a thread pool with a worker cap, and we'll meet that API in a minute. And if you need thousands of concurrent connections instead of 20, that's where Essentio enters the picture, 1 thread, an event loop, and tens of thousands of sockets. Same principle though, it only wins when the workload is waiting. Async does nothing for CPU-bound code either. So let's carve the rule in stone, because these 2 benchmarks are the whole story. First question, always. Is my workload CPU-bound or IO-bound? Is the time spent computing or waiting? CPU-bound, threads can't help you. The GIL serializes them. You want processes. IO-bound, threads are perfect. The GIL steps aside while you wait, and processes would just add overhead. Threads for waiting. Processes for computing. If you remember 6 words from this video, make it those 6. Now, raw thread and process objects are great for learning, but in real code you want the modern interface, concurrent.futures. It gives you 2 pool classes with the exact same API, so switching strategies is a one-word change. Our workload this time is deliberately chunky, 100,000 rounds of SHA-256 hashing per item, proper CPU work, 32 items. 3 ways to run it. A plain list comprehension, our baseline. A ThreadPoolExecutor with 4 workers, using pool.map, which works exactly like the built-in map, but distributes across the pool. And a ProcessPoolExecutor, and I want you to appreciate this. It is the identical line of code with 1 class name swapped, though with statement handles all the startup and teardown for both. And run. Plain loop, 3.11 seconds. Thread pool, 3.18. Actually a hair slower. The GIL plus a little pool bureaucracy. And the process pool, 1.02 seconds, 3x faster. And that's including the cost of spawning 4 fresh Python processes. On bigger workloads, that overhead amortizes even better. 2 more tools in this API worth knowing. Pool.submit hands you back a future for a single task, and as completed lets you consume results in whatever order they finish, perfect when tasks have wildly different sizes. And pool.map takes a chunk size argument, which batches many small items into each round trip. If you must map over thousands of small tasks with processes, a generous chunk size is often the difference between a win and a faceplant. Before you go wrap everything in a ProcessPoolExecutor, though, I owe you the dark side. Processes are not free. Starting one means booting a whole new Python interpreter, and every argument and every result has to be pickled, shipped across the process boundary, and unpickled. So here's a deliberately brutal test. A tiny task, x plus 1, called 1,000 times. Trivial work, done 2 ways. Look at this massacre. The plain loop finishes in 150 microseconds. The process pool takes about half a second. That's over 3,000 times slower for the same result. All of it is overhead, spawning interpreters and pickling integers back and forth. Parallelism has a price of admission, and tiny tasks can't pay it. The rule of thumb: if one unit of work takes less than a few milliseconds, don't ship it to another process. Batch it up first, or just run the loop. And one Windows-specific landmine while we're here. On Windows, and on modern Mac OS, new processes start with the spawn method. The child boots a fresh interpreter and re-imports your script from the top. If your pool creation isn't guarded behind if name equals main, the child reruns the pool creation too, which spawns more children, which spawn more children. Fork bomb, by accident. That guard you keep seeing in my scripts is not a style choice. It's load-bearing. Pickling has sharp edges of its own, too. Everything crossing the process boundary must survive pickle, which means lambdas and locally defined functions can't be pool tasks at all. You'll get a pickling error before any work happens. And big arguments hurt twice. A 100 megabyte array gets serialized on the way out and deserialized on the way in. If you're shipping serious data between processes, look at multiprocessing's shared memory, or better, keep the data in the worker and only pass small descriptions of the work. Let's make this concrete with the 3 situations you'll actually meet at work. I'll keep a little cheat sheet as we go. Case 1, the web scraper. 200 pages to download. Each request spends 99% of its life waiting on the network. Classic I/O bound. A thread pool with something like 16 or 32 workers will get you an order of magnitude, easily, and the code barely changes. Case 2, the batch cruncher. Resizing 10,000 images, parsing gigabytes of logs, hashing files, feature extraction. The CPU is pinned the whole time. This is ProcessPoolExecutor country, with workers set near your physical core count, and each task chunky enough, think seconds, not microseconds, so the spawn and pickle tax disappears into the noise. And case 3, the one nobody tells you about, mixed pipelines. Download 200 files, then parse them all. The pro move is to use both. A thread pool fans out the downloads, a process pool crunches the parsing, and a plain queue or just 2 map calls in sequence connects the stages. Match each stage to its own bottleneck instead of picking one tool for the whole job. Let's assemble the full decision kit. Rule 1, diagnose first. Profile, or just reason about where time goes. Waiting on network, disk, or a database, that's I/O bound. Burning CPU on math, parsing, compression, that's CPU bound. Rule 2, I/O bound means threads, a thread pool executor with a healthy worker count, or a Cincio if you're going all in on high concurrency. Rule 3, CPU bound means a process pool executor with workers roughly equal to your core count and chunky tasks so the overhead amortizes. And 2 footnotes that save real pain. Libraries like NumPy release the GIL inside their C loops, so heavy numeric code sometimes scales fine with plain threads, measure before assuming. And Python 3.13 ships an experimental free threaded build with no GIL at all. It's not the default, and most libraries are still catching up, but the ground is moving. The rules you learn today are the rules of CPython as it actually runs in production, now and for the next several years. So, the scoreboard. CPU-bound work, for threads gave us nothing, for processes gave us 3.5x. I/O-bound work, 20 threads gave us 12x, and processes would have been overhead with extra steps. Tiny tasks, the process pool was 3,000 times slower than a plain loop. Threads for waiting, processes for computing, nothing for tiny tasks. 3 rules, backed by measurements you watched happen. And maybe the deepest takeaway of all, nobody in this video guessed. We asked a question, wrote the smallest honest benchmark that could answer it, and let the clock decide. Do that with your own workload before you commit to an architecture, because your data, your libraries, and your machine will bend these numbers in ways no YouTube video can predict. The rules travel. The exact numbers don't. If the benchmarks earned it, a like genuinely helps the channel, and subscribe for more measured, no mythology deep dives. Next time, we build a real-time chat app on WebSockets in Python, live connections, broadcast, the whole thing. See you there.